Good morning, chemistry students. How are you today? Thank you for joining me. And you need this note sheet out. I think it's page 21, 22 in your binder. You also need a calculator, something to write with, of course, and your periodic tables. Go ahead and dig all that stuff out. All right, today's topic is empirical molecular formulas. It's really easy. You guys are going to love this. So, what is an empirical formula? An empirical formula is a formula that gives the smallest, whoops, let me get a pen, the smallest whole number ratio of elements in a compound. And a molecular formula is a formula that gives the actual number of each element in a compound. Okay, so let's see if we can see what that means. So we have three examples. First compound is hydrogen peroxide. So the stuff in the dark bottle that you put on your boo-boos and it bubbles. Okay, so its formula is H2O2. All right, so that's its actual molecular formula. That's what hydrogen peroxide is. Two H's, two O's, covalently bonded. Its empirical formula, however, would be if you could reduce those subscripts. So H2O2 can be reduced to HO. Or if you want, you can put those ones in there, H1O1. You see how it works? Okay, so let's do glucose. Glucose is C6H12O6. That's its actual formula. 6 carbons, 12 H's, 6 O's, all covalently bonded. Can you reduce those subscripts? 6, 12, 6 can be reduced to C1, H2, O1, a 1 to 2 to 1 ratio. So that's its empirical formula. Okay? And let's see, we got water. Water is H2O. Can we reduce those subscripts at all? Can't really reduce it anymore, so the empirical formula is also H2O. So sometimes the empirical and the molecular, they're the exact same thing. Okay? So we get what it is. Now what do we do with this information? All right, so oftentimes in chemistry, we're trying to identify some unknown substance. And one way to do that is we collect some data and we have the percent by mass information for this unknown substance. So it's 24% potassium, 35% manganese, and 40.5% O. Okay, so from this, can we figure out what its formula is? Like, is it K1Mn2O4? Or is it K3Mn4O7? Okay, so we don't know. We're going to figure that out. All right, so there's a couple steps. They're very easy to follow. First of all, since we often have this percent by mass data, the percents aren't very useful. Okay, we need to get those percents into grams. Okay, well, that's really easy to do because whatever this unknown sample is, its percent by mass is going to be uniform throughout the entire sample. So we just need to pick an amount of sample. The easiest amount of sample to pick is probably 100 grams because what's 24.75% of 100? It's 24.75 grams. So if you assume 100 grams, then those percent values, they just automatically turn into gram values. And that's really, really, really easy. You don't have to assume 100 grams. You could assume 1 gram, 10 grams, 72.89 grams. It doesn't matter. You just have to take those percentages and get those mass values. Okay? So that's step one. Sometimes they give you percents, like in this example. Sometimes they just give you the gram values, and you can skip step one. So that's fine. All right, once you have the gram values, that's great. But I really can't tell the relationship between potassium and manganese and O from mass because each one of those atoms has different mass, so I don't know how many there is of each. So the key here, as always, is if you have gram values, convert them to moles. And if you convert to moles, then you have this idea of how many of each element there is, and then you can get yourself some subscripts and a formula, okay? The take-home message is get the gram values of each element, convert the grams of each element to moles of each element. All right, so we're going to do that. So I'm going to start with potassium. Let's see, 24.75 grams. Yeah. And we're going to convert that to moles. Okay, and I'm going to look up potassium on the PT. Put grams on the bottom. 1 mole on top. 1 always goes with mole. 1 mole of potassium has a mass of 39.10 grams. All right, just like always, the grams of potassium cancel out. You guys can divide. I'm going to do that too. Let's see here. 24.75 divided by 39. Whoops. 39.10 is bazam. 0. And I'm going to take this to the right number of sig figs too. So there's 4 sig figs here, 4 sig figs here. So 0.6330, I would say. Yes. All right. So can you guys do that for the other 2 elements too? So now we got manganese. I just like to say it that way. I don't know why. 34.77 grams. okay, of manganese. Grams on the bottom, 1 mole on top. Ooh, I like my penmanship, don't you? Okay. Manganese has a molar mass. I look it up on the periodic table. 1 mole of manganese weighs 54.94. Okay. So same thing, grams of manganese cancels grams of manganese, and you are left with moles. So I'm going to punch that puppy in as well. 34.77 divided by 54.94. And that is also 0.63. I'll round that up to 29. Okay, now take a minute here and appreciate what just happened. When I looked at their mass values, I was like, oh, 24 grams, 35 grams, it's not really 1-to-1. I don't really see a relationship. But once I converted them to moles, all of a sudden, oh, I have like equal moles of potassium and manganese, so that must mean they're in a 1-to-1 ratio in this formula. Okay, so that's the magic. Okay, you got to take those gram values and get to moles. Moles is where you're going to see the relationship. All right, and the plot thickens. Let's take a look at O. So O is 40.51. Okay, and oh, be careful. I know oxygen's diatomic, right? It's one of the magic 7. O2 is how oxygen gas exists. But in compounds, O just stands alone. Okay, so diatomicness does not exist when we're doing empirical formulas. So I got grams O, 1 mole O, molar mass of oxygen. You guys probably have that memorized by now, 16. Okay, so I'm going to take 40.51 and divide by 16. And that guy looks like about 2.532. Yes? Okay, so you guys, now we have our 3 mole values. All right, so you can kind of see like a relationship developing already. The K and the Mn are in a 1-to-1. You can kind of see, okay, it looks like you can see a relationship with the O as well. But to really, really, really see that relationship clearly, we're going to do step 3. Step 3, find the relationship, find the smallest whole number ratio between the elements by dividing each mole value by the smallest number of moles calculated. So I got these 3 mole values. The smallest one is this middle one. So basically, I'm going to set this guy to 1, okay, because I'm going to divide through by itself. So I'm setting the manganese to 1, okay, and then I'm going to divide everything by that smallest mole value. So I'm going to divide this guy by that same number, which that also goes in once, and then this guy, 6329. You can punch that in if you want, 0.6329. Goes in about 4 times, and it comes out pretty exact. Okay, so now what you guys see here is by dividing by the smallest mole value, set the smallest one to 1, and then anything bigger than that is going to be some whole number. All right, well, look at that. So that, my friends, is basically the subscripts for this formula. So it says round to the nearest whole number. These numbers represent the subscripts in the empirical formula. So the formula for this compound would be K1, Mn1, O4, which actually, you could name that compound, that's potassium permanganate. MnO4 is one of your polyions. Okay, so you guys see how it works. So if you got percents, make sure you turn those percents into grams. When you have grams, you got to convert to moles. Once you convert to moles, divide by the smallest mole value. You can see the relationship, and you got yourself an empirical formula. Okay, pretty easy, right? Now there is one small complication. So in this problem, the numbers came out perfect. It was easy. We were just done. Sometimes the numbers don't come out so nicely. Okay, so let's say in another example, when you divide it by the smallest mole value, let's say you got 1 to 1.5. Okay, so sometimes you can round to the nearest whole number, okay, if you're really close to a whole number, but 1 to 1.5, you're kind of too far from the nearest whole number to round. Okay, so these are kind of some cutoffs. Basically, if the decimal is 0.1, then you can round down to like the nearest whole number. If the decimal is greater than 0.9, then you can round up to the nearest whole number. But if it's between 0.1 and 0.9, you probably need to find some multiple to get a whole number. So for instance, if it was 1 to 1.5, what can I multiply both those numbers by to get whole numbers? Okay, and you guys probably think you can multiply by 2. So then instead, I would have a 2 to 3 ratio. You guys see how that works? So we just kind of scale it up to get whole numbers. Now, and folks, I'm going to use friendly decimals. So maybe I might give you something like a 1 to 1.33. Okay. And you're like, oh, well, you could go 1 and round that down to 1 to 1, but that's a lot of rounding. So what we do instead, what can I multiply by to get a whole number? To multiply by 3. So 1 times 3 is, you'd have a 3, and 1.33 times 3 is basically 4. So you'd have a 3 to 4 ratio. You guys see how that works? So that's kind of tricky, but I'm going to have you guys do this example. It says determine the empirical formula for this compound. It's going to utilize this principle, okay? So I want you to go ahead and whoever's running the video, pause it. Go ahead and do this example, okay, and see if you can figure out how to handle the ratio, okay? All right, so pause it and get going. Okay, so I hope you gave it your best go, but let's see how you did. So you take the hydrogen, 18.7.17, and they just gave you the gram value, so you didn't have to worry about percentages. Converted to moles, I got 17.99 moles. Did the same thing with the carbon, 96.09 grams carbon, converted to moles, got 8.001 moles. Okay, and then we divided by the smallest mole value. So that was the 8.01, so we set this guy to 1, divided this guy by 8.001, and the ratio came out to 2.25. Okay, you say to yourself, oh boy, is that too much to round? If it was 2.1, we can round down to 2.0. If it was 2.9, we can round up to 3, but 2.25, kind of in the middle. So we're going to find some multiple. What could you multiply 2.25 by to get a whole number? Okay, and hopefully you guys came to the conclusion that you can multiply by 4. Okay, so make sure if you multiply 1 by 4, you multiply the other part by 4 as well. So in essence, you end up with a 4:9 ratio, which is a nice whole number. So the empirical formula for that guy, H9C4. Okay? All right, you guys are doing great. Okay, so we got one more thing to learn. All right, so what about molecular formulas? Okay, so this is super easy. So the truth of it is the molecular formula is always some multiple of the empirical formula in both mass and subscript. Okay, so I'm just gonna go back to this very first part. You guys remember this little table? So like H2O2, if you add up the molar mass, let's see, oxygen, and there's 2 of them, so that's 32, 33, 34, because each hydrogen is 1. This guy's molar mass is 34, right? The empirical formula, let's see, only 1 O, so that's 16, and 1 H, so that's molar mass of about 1, so its molar mass is 16. So you guys see what I mean? So the molecular is some multiple of the empirical, because you multiplied the empirical by 2, and it's also some multiple in terms of the mass. Okay, so if you double the subscripts, you're going to double the mass. What do you think? Okay, so if that makes sense to you, let's see how we apply it to the math. So for this example, let's say the empirical formula was CH2O. What is the molecular formula if the molar mass of the actual substance was 180? Okay. So basic idea, you just need to find the relationship between the molecular and the empirical by looking at their mass. So I'm going to take the molar mass of the molecular, which is always given, okay? Like in this problem, that's the 180, okay? And I'm going to divide by the molar mass of the empirical to see what's the relationship between those. What's the multiple, okay? So if I do that here, 180.06 was given. Okay, grams per mole. And then if I add up 1C, 2H is 1O, let's see, we get 12.01. That's a C. 2 H's, right? So 2 times 1.01, because that's 1H, so we got 2 of them, plus 16. Okay, that's the molar mass of oxygen. So if you add those up, 12.01 plus 2.02 plus 16 comes out to about 30.03. Okay, well, how many times does 30 go into 180? Okay, and the answer is 6 times. Okay, that's the magic multiple. So guess what? If the molecular is 6 times that of the empirical in terms of mass, then it's going to be 6 times that in terms of the formula. Okay, so if I take 6 and multiply it by the empirical formula, the molecular formula for this guy would be C6H12O6. Okay, so that's kind of the process you go through. So bottom line, I want you guys to go ahead and give it a try. So it says find the molecular formula for a compound that contains 4.90 grams nitrogen, 11.2 grams O. The molar mass of the compound, so that would be the molecular, is 92. Okay, so folks, 2 big steps here. 1, I want you guys to follow the steps to determine the empirical formula. And then 2, once you get that, then I want you to do this new stuff here and figure out the formula for the molecular. Okay, so there you go. Again, I want you to pause the video. Go ahead and give this a stab. Go ahead and give it a try. Okay, take about maybe 7 to 10 minutes. Okay, and then resume the video, see how you did. All right, so okay, I'll stop singing. You press go when you're ready. All right, Bazam, how'd you do? So, empirical formula first. So we took 4.90 grams of nitrogen, converted it to moles, right? 0.350. We took 11.2 grams of oxygen, divided by 16. Remember, diatomic doesn't count when you do empirical, and we converted it to moles. Pretty clear to see the relationship, okay? So you divide it by the smallest mole value. We set the n to 1, because that was the smallest mole value. And then we took that small number and divided it into this oxygen value, and it went in twice. So the empirical formula for this compound was N1O2. Okay, so we got that part. Yes? Good? Easy? All right, so then how do we go from the empirical to the molecular? Well, then it's always given that they gave us the molar mass of the molecular, which was at 92.0 grams per mole. And then we divide it by the molar mass of the empirical, which we calculate. Okay, so we took 1 nitrogen, which is 14.01 grams, and 2 oxygens, which is 2 times 16, added that up, and it came out to 46.01. Okay, so then we compare those numbers. So the empirical formula went into the molecular formula twice. So that, my friends, is the multiple. Okay, so that means that the empirical formula, the molecular formula is 2 times that of the empirical. So we take that 2 and we multiply the empirical by that magic multiple, and this is the molecular formula. Okay, so that's the actual formula N2O4. What do you guys think? All right, so there's going to be some practice so you guys can do what you are assigned. Thank you so much for listening. Have a great day. Thanks.